Cool. Quick and sounds good. So quick announcements. The Zoom recorded attendance is in a delay to Moodle, so don't worry about it not showing up on Moodle. If you attended on Zoom, it's automatically recorded. So for the all Zoom lecture, or if you're attending Zoom during the class period, it's recorded. Don't worry about it. It'll eventually be logged in Moodle, but we have the recorded, right? It's automatic from when you log in to the seminar. The second thing, a lot of questions about the alternative seminar forms. Nothing's changed as described in the syllabus. You fill out the form on Moodle. We get the form. Unless you hear back, it's approved. Remember, alternative seminars are other technical seminars, conferences, and things like that, right? Alternative seminars aren't like I have lunch or a brunch meeting that time period, right? And so you just have to fill them out. You're allowed up to 3. So fill out 1 for each time you're going, and you'll see there's basically 3 options on Moodle. So the first one you fill out is alternative seminar 1, 2, and 3. And those are your 3 for the semester. Please try to do them before you go, right? And they're just alternatives. They don't have to be on the same day as the seminar or as colloquium as 801, right? They could be on any day. They're just replacing one of your class periods. Questions? Cool. Thank you.
Right, well, it's my great pleasure to introduce today's speaker. Today's speaker is Dr. Khaled Khasawneh from George Mason University. Khaled is an assistant professor in the Electrical and Computer Engineering Department. His research interests are in microarchitecture security, malware detection, and recently on hardware support for trustworthy machine learning. Welcome, and please take it from here.
Thank you. Thank you so much for the introduction, and thank you everyone for joining. Let me just sit down. Okay. In today's seminar, we'll talk about trustworthy machine learning from a computer architecture perspective. So let me start the talk by talking about trends in security, computer architecture, and machine learning. And then I'll explore research opportunities in these intersections, and then I'll give you examples from our recent works in these areas. In computer security, cybercrimes is the fastest growing criminal activity in the United States, and they're growing in size, cost, and sophistication. And this shows that cybersecurity is a fundamental requirement that we should take into account when designing computing systems on par with performance, functionality, and power consumption. In computer architecture, a few years ago, there was this vision workshop. It's called Architecture 2030, and they kind of envisioned, what the computer architecture community will be working on for the next 10 years. So there is a wide acceptance that Moore's law is ending, so we no longer can shrink the transistor technology to get performance. So we'll see a lot of specialization happening at scale, where we have specialized accelerators for specific important workloads that we're building, and we see TPUs is an example of them, for machine learning applications. Also, we'll see wide use of cloud services, and then machine learning will be becoming a more and more important workload. And then we'll see this as ChatGPT and Bard are coming into the picture. And the last thing, also because of this Moore's law is ending, we're going to see a paradigm shift where we move into quantum computing or to DNA computing technologies. Now, in the machine learning side, we started to see more sophisticated, machine learning are able to do more sophisticated tasks. So as ChatGPT, I think most of the people in the room know what is it. So we have also GitHub Copilot, which can write you code. And then we have now multimodal models, where you can not only have text as an input, but image, text, and different input data to the models. Also, it's becoming more easier to adopt. So we're seeing big companies have this no-code, low-code services, where you can train machine learning models by using graphical user interfaces. So anyone can now train models. And then even these large models are becoming faster to train, right? And then all of this led to global market growth that is expected to keep growing with projection of market, the market to reach to more than 200 billion by 2029. Okay, so given these trends, my research as well as my teaching interest is at the intersection of these three major areas, which is computer architecture, machine learning, and security. And then I'll walk you through, what are the research opportunities at first, the pairwise intersections between these areas, and then I'll talk about the intersection between the three of them and give you examples from our work there. So what are the research opportunities at the intersection of architecture and security? So I see this as two directions. There is a direction of attacks and direction of defenses. From the attack direction, it's basically how you find vulnerabilities that originate in the hardware or architecture. Examples of those is side channel attacks. Okay, example of those side channel attacks, transit execution attacks. If you guys know Meltdown and Spectre attacks or type of transit execution attacks, fault injection and hardware Trojans. On the other side, from defenses side, I see it as two categories. The first one is do no harm. So just how do we design architecture to avoid these vulnerabilities that we find? And then the other category is how architecture can help software by designing security, providing security abstractions or mechanisms that help security in general, or computational support for expensive defenses that are implemented in software. And example of security abstraction is, a trusted execution environment such as Intel SGX, and we have ARM also built this environment using technology called ARM TrustZone. The other intersection is between computer architecture and machine learning. And here we have symbiotic relationship where we have architecture for machine learning and machine learning for architecture. So what is this? For architecture for machine learning, so we're building architecture to support the machine learning workload because training and inference is computationally intensive. So we need hardware to support the needed computations. And also for specific applications, we have other constraints such as real-time response and also low power. The other, for machine learning for architecture, we're seeing now wide adoption of machine learning taking decisions at the architectural level, whether it's at design time or during runtime, where it's prediction, security, reconfiguration. At the last pairwise intersection is security and machine learning. So in the first direction is how security, the security of the machine learning model itself, the machine learning system. So what are the threat models facing these systems, and how can we ensure security and privacy of these systems? And then also we can use machine learning to help security, such as malware detection, fraud detection, and so on. It's okay. So now the focus of this talk will be at the intersection of all of this. And now we'll look at what is at the intersection of computer architecture, machine learning, and security. So I see it as we have attack directions where we have, first is we exploit, if machine learning is used in architecture, we exploit machine learning vulnerabilities to attack the architecture. And then also you have attacks where there is microarchitecture vulnerabilities or architecture vulnerabilities. We use them to attack the machine learning system. And then from the defense side is how we can build efficient defenses using the hardware support. So in this talk, I'll give three examples. The first example will be attacking machine learning using the architecture. So basically, we have malware detection. The application we're using is malware detection at the architecture level, and how can we build evasive malware that can evade the detection? And then we have, in the other direction, I'll talk about two examples for hardware support for trustworthy machine learning. One example to help security of machine learning, and another example how to help the privacy of machine learning using hardware support. Okay, so let's get started. So the first one is called a paper called Evasion Resilient Hardware Malware Detectors. So malware is everywhere, and we can see, numbers of malwares is increasing every year. There is new malwares that we find. And remember, this is what we see, right? This is what's been analyzed, and we know that this is malware. There is a lot of malwares that are in the wild, and we don't know about them. And also, if we want to look at the malware trends, so we're seeing now, the ransomwares are getting decreased in the wild, and we're seeing now more malwares that are cryptojacking and IoT malwares numbers are increasing. So, against these attacks, usually, traditionally, we have antivirus, which are static-based malware detection, but they only can find the malwares that they know about, that have been analyzed. They can't find the new malwares or detect new malwares or zero-day exploits. Then the other one is dynamic monitoring, and it's not widely, it can detect 0 days because it looks at the behavior of the programs, but it's not widely adopted because it's computationally intensive to monitor all the programs all the time. So that's why people move to using the hardware support to support this problem, computationally intensive of monitoring the programs and detecting malware. And they came up with hardware malware detectors. So hardware malware detectors basically use machine learning to detect malware as a computational anomaly. And the interesting thing is that they use subsemantic features from the hardware, not semantic features at the software level, such as number of cache accesses, number of hits and misses in the cache, number of branch misprediction. And then the interesting thing about these detectors, it can be always on without adding performance overhead since they are at the hardware. And there are a lot of papers that published in leading conferences in the community that showed that these can work. And this is great, but the interesting thing is that Intel in 2021 came up with this technology. It's called Intel Threat Detection Technology that uses hardware performance counters to monitor the hardware and then provide interfaces to build machine learning models to take this data monitored and run it on the integrated GPU to detect malwares as a computational anomaly. And this technology was used by Microsoft Defender for Endpoint to detect cryptojacking attacks. Okay, so now industry adopted this, but it's great, but also we want to think about attackers would adapt, right? So how the next generation of attacks would look like. And that's basically the contributions of this work. So the first question we ask is, can malware evade these detectors, right? And we showed that the answer is yes. We were able to reverse engineer them to understand how they work. And then we were able to develop evasive malwares that can evade the detection. Since the answer is yes, then the next question is, how can we build more robust detection to resist this evasion attacks? So, and we were able to come up with randomization-based strategy based on learnability theory called backpack learnability theory that makes the reverse engineering part harder and thus the evasion harder. Okay, so now the first component of the attack is the reverse engineering. And the challenge like we faced is that we don't know, we see the detectors as a black box. So we don't know the detection period, the features used, or the detection algorithm that is used. So what we've done is we trained different classifiers using different inputs. And we'll show you how we did this training and then drive specific parameters as an optimization problem. So how we train different classifiers is, I think I removed the details, but basically we prepare attacker would prepare like malwares and benign programs, then would run it on this detector and monitor the output. Then we use that output of the black box detector along with the input sample to train a new detector, and we call it the reverse engineer detector. And then we test it against this with a different data set, test data set against this black box that we're trying to reverse engineer. And then if the output of these two detectors matches, that means we're capturing the functionality that this targeted detector that we're trying to understand and reverse engineer, we were able to capture its decision boundaries. So we tried this with different feature spaces, one based on the instructions only, memory and architecture. And even we tried one with like all feature spaces. And you can see that we were able to have like really high reverse engineering accuracy. So which means, current generation of HMD can be reverse engineered. So we have a kind of a substitute model that capture the model of this targeted detector. So now we have this reverse engineer detector.
I'm sorry.
Yes.
So can you give an example as to what, can you just one
Yes.
example of these beasts that that comes and attacks the,
So still we're not attacking now. Right now we're trying to reverse engineer.
right,
So reverse engineer, so we have this black box, right?
right,
So we can give it out input and see the output.
okay,
It's a black box, but we still can give it input and see the output. So the attacker would prepare samples that are malwares and samples that are benign, and then run it through this detector classifier and record the labels. That not the true labels. We don't care about true labels. We care about how this model labels them. Okay, I get these labels, and then with the input that I provide as an attacker, and then train a new model with these to capture the behavior of this. Does that make sense?
maybe, go ahead.
Follow-up.
Yeah.
Did you synthesize your own malware, or did you use like a?
That we use from public, we use like malwares from a website that is down right now. It was called like malware DP. And then we verified, we ran these malwares, and then it triggered the intrusion detection system in the university. So I had to set up like an own like separate isolated cluster to run the malware attacks in them. Okay. So again, we were able to reverse engineer them with a high accuracy, and we showed that current generation of HMD can be reverse engineered. So now we have this reverse engineered model of substitute model, and we want to use it to attack and just and to use it for attack. The challenge we had is we don't have malware source code because we took malwares from the wild, and we couldn't decompile the malware because it was obfuscated. So we came up with a new approach to modify the malware and try to make it evasive, where we take the malware executables and run them to get the dynamic trace of instructions. From the dynamic trace of instruction, we built a dynamic control flow graph, and then we inject instruction in the inject instructions at the dynamic flow graph level. And then the best strategy that worked for us is injecting instructions at the block level of the dynamic control flow graph. So to simplify, how we did the injection, I'll talk about if the reverse engineering model is logistic regression. So logistic regression is defined by a weighted vector. And then we add instructions whose weights are negatives to impact the output to classify, to lower the probability of the output being a malware. But we do this also with care, because you want the malware to keep their malicious functionalities, right? So when we add instructions, we want to make sure it doesn't affect the state of the program, so that the malware can still keep the malicious functionality that they're intended to do. So with this strategy, so we were able, but by just injecting one instruction per basic block, we were able to drop down the detection accuracy from 100%, where we just got the malware that are correctly can be classified by that classifier, and we try to make it evasive. So we were able to drop it to below 15%. And then as we add more instructions in the basic block, we can make all malwares evade the detection. We also tried random injection to verify, like, do we need to go through all of this to make malware evasive, or can we just add random instructions? And we saw that random instruction strategy did not work. So we proved that current generation of HMD is vulnerable to this evasion attack. Yes.
So can you really be more insight on why you insert just say one instruction in a basic block, then you can evade the detection? It seems that the detection probably deselects the wrong feature or something.
No. So first of all, like if I'm the attacker, I design the malware, I can rewrite the program, right, and avoid using these detection features. But like here, we went with this approach only because we're working with real malwares that we can't access the source code of it, and that we went with this other approach to be able to inject the malicious instruction and change the feature. And then in terms of features, these are hardware features. They monitor the computational anomaly, right? So they monitor, from computation perspective, how this program behave. So you can implement the program in so many different ways, right? Like, and then you basically were trying to change this computational signature so that the detector can't identify
That's
this.
what I mean, like the signature seems to be wrong, so just give a can you give a more concrete example, what instruction you inserted, like, like this, basically no ops or.
I see,
node or
yes.
I think probably the feature extraction, we are not extracting the true signature of this.
Okay,
model.
so yeah,
We got
so
some superficial features.
I got you. So I just want to show you that, because this is dynamic monitoring, and so you have a monitoring period. So we, for the monitoring. So you don't run the program until it ends and say this is a malware or not. You will split it into periods and then do a detection at the end of one period. So within that period, for example, let's take ransomwares, right? They're trying to do a lot of encryptions in a small amount of time, but why, right? You can split this encryption over, like the detection period. The ransomware will take a longer time, but can evade the detection, right? Let's say you can do, one encryption every minute, right? Now the signature is gone, right? From because you do encryption for communication, for email communication, for internet connections. So you still use encryption, but you don't use it intensively in a small amount of time. Malware does that. So you pick that signature. And then if you just, you can change the malware to change that signature, computational signature. So we're talking about subsemantic features. So we're not looking at the code itself and know that they have a loop. We're trying to encrypt the whole file. We just see the instructions that go through the processor, and you don't have a big picture of the whole program.
Yeah, that seems to me like this hardware, the existing design, the feature is overfit to that particular malware. That seems to be the problem. But anyway, I think I've said enough.
So in this, like the data set we prepared, we have we try to get pick different families, but this problem is not just for malware, right? Like it's adversarial examples is known in the machine learning community where you can perturb the input to force the classifier to change the output. So it's not only in this application where we see it in images, like in object detection, and a lot of other applications. So this is a known problem or vulnerability in machine learning systems.
So that's not what you're doing. It's not that notion of adversarial that's used in machine learning.
It's the same, but like
how do you minimally perturb the input to get a completely contradictory output?
Yeah, so now it's different applications, so you have different constraints. In image classification, your goal is to minimize the nodes so that for a human eye, the image did not change, but the classifier would misclassify it. But in malware detection, your challenge is different, right? Because human eye cannot tell that this is a malware or not. It's running in the background even. But the challenge is how to build these without changing the functionality. You need the malware to still keep this malicious functionality, but I want to change the code, right? So how to change it while keeping the functionality is the challenge. So you have different challenges because this is a different application. But the vulnerability is the same, that machine learning models, you can move this across decision boundaries by adding some noise. This is because we're using instructions as features, this is why we had to do instruction injection. And we can even substitute the instruction if we have access to the source code. But since we didn't, and we want to experiment with real malware, that's why we did this approach. Okay, thank you so much for the discussion. Okay, now let's move on. So we looked into how can we resist this evasion, and then we end up looking at the paper. It introduces the pack learnability theory, and then this theory they prove that the error introduced into reverse engineering component of the attack is bounded by how often if you're using multiple classifiers, how often these multiple classifiers disagree. So we took this and we try to build diverse detectors, so a pool of diverse detectors, and then how it works is that we split detection periods, at the end of each period, you get a feature, and then you run it through this RHMD construction. You select a detector randomly, and then get the output. And we do this for every detection period, where we select a random detector, and then we diversify this detector by changing the features or changing the detection period for these detectors. So we tested these detectors against, first, like we want to test it, can it still classify the malwares, right? Non-attack malware, right? And we're able to show that, we use different combinations of detectors where we, 2 or 3 detectors where they look at different feature spaces. And then we also try to do it with also having 2 versions of each feature space where the detection period also change. And we can see that still we maintain high accuracy in detecting the malware. And then we tried simple attacks where we add 1 instruction at each basic block. And remember this, reduced the detection accuracy to less than 15%. And as we move into more diverse detectors, we can see that we can detect even evasive malwares. And then we tried more intensive attacks where we had 10 instructions per basic block, and we still can maintain the detection of these evasive malware. Since we work in the hardware, right, overhead is also a problem. So we want to evaluate our solutions against how much overhead to add to the system. So we integrated the solution into an open core, simple open core. And then we optimize the neural network implementation of detection to use 1 perceptron over time, and then do the detection. And then RHMD with 3 detectors increased the area by 1.72% and the power by 0.78%. And remember, this is like a 5-stage core. It's not like a really big core. So if you compare it the overhead to current processors design, this will be much less. Okay, so now we're done with the first example, which is attacking machine learning that is used in computer architecture. And I say computer architecture, but this also applies to systems, okay? So, any system. So we showed in another paper that for resource provisioning systems that, when you submit a task or a VM or work to a cloud environment, a cluster, this resource provisioning system can send this task or VM to a specific resource based on the needs. Some of them are based on machine learning, so we're able to exploit this to do collocation attacks. So if you're targeting a specific applications in the cloud or a cluster, you can exploit the same vulnerability to collocate your VM with targeted VM. If you're targeting financial, applications or the privacy applications, any private data or specific application, you can use this attack to collocate with that targeted victim application. Okay, so now the other example we start to talk about now hardware support for machine learning security. The first one is for securing ML. So machine learning is everywhere. Yeah.
Out of curiosity.
Yes.
You keep referring to vulnerability.
Yes.
And at a high level, though,
yes,
a vulnerability can be, for instance, in the data exchange among the different blocks at your hardware level.
Yes.
Or it can be something intrinsic to some block.
Yes.
So which one is?
It's the machine learning model itself. So when I started my talk, I talked about different directions.
Mm-hmm.
So the ones that you're referring to is microarchitectural vulnerabilities. And these are exploiting the machine learning system vulnerability. So it's not specific to the architecture. This, as I said, there's different application images, the malware detection. We talked about also resource provisioning system. All of them uses machine learning, so they're vulnerable to adversarial examples. Okay. So and deep learning. Oh, sorry, I'm off topic now. So okay, now we'll talk about approximate computing to secure machine learning models. So machine learning models is used. How much time do we have left? So they know.
I think you can have around half an hour more. So.
Okay. So deep learning models, offer exceptional performance in different tasks, in healthcare, object detection. So and then they're vulnerable to adversarial attacks. So in the image domain, okay, what is our adversarial attacks? So adversarial attacks is image manipulation that imperceptible to the human eye, which can be, which can alter the output of the machine learning model. So for example, the classifier would classify this image as a panda with, a good confidence. But if you can, using adversarial attacks, you can add noise. So for the human eye, this still looks like a panda, but for the classifier, it classifies it as a gibbon with a really high confidence. Okay, so these are called adversarial examples or attacks. So, and then this has serious implications, especially for safety critical and security sensitive applications. So, and this was also demonstrated in like a physical world, right? So, imagine like a autonomous car where you can put like tape on the stop sign, and then stop sign will be classified as a speed limit. So you can see that this is a serious vulnerability that we should take care of. So there is a lot of defenses that was proposed like in this from the machine learning community in this domain. So there are defenses at design time and defenses at runtime. In design time, it's mostly during the training. How can we make sure the training know about these attacks, and then train them with the expectation that we know we have adversarial examples in the training set, and then this would strengthen the model, and then we use this model, the strengthening model at inference, to do the classification. We also have other category where we have input filtering, so they try to filter the noise that you inject at the image before it goes to the machine learning model. We have also detection. We look at features in the machine learning model, try to detect. And then at the end, we have randomization-based models that work during inference, basically. However, at design time, you're always required to retrain the model with the, with these strategies in order to make it harder. And also, it shows that it's widely known in the community that this would reduce the utility, which is the accuracy on benign data, not the adversarial data. And then we have, and at runtime, all the defenses will lead to higher computation, right? You're adding inference is known that it's, machine learning in general, training and inference is known to be computation intensive, but we're adding more computational things that needs to go along with it, which will introduce higher computation, higher latency, and more power consumption, which make it, for these defenses, hard to adapt, especially in resource-constrained devices, right? So we started to think, we have this randomization-based defenses. So how can we add randomizations for free from the hardware, right? So we came up with this idea that's called defensive approximation, where we leverage approximate computing to enhance the CNN robustness against adversarial attacks. So we basically inject data-dependent noise with the convolution calculations and using an aggressively approximate multiplier. By this, we were able to avoid retraining the model, fine-tuning them, do pre-processing at the input, or it's not attack specific. So we tried it against all available attacks and it's working. Also with the addition of reducing the energy and the latency of the machine learning model. So how this looks like, so this is a generic view of a CNN. So we have convolution layers and then we have fully connected layers. So at the end of the convolution layers, we get feature maps. So we applied this approximate multipliers at the convolution layers computations, the MAC computations. And then if you look at the noise that these multipliers would introduce, it's data dependent. So as the multiplier and MAC values increase, it adds more noise to it. Then you get basically at the end, but when you do this use this approximate multiplier, you get approximate feature maps. And then we noticed that, okay, if we use this, then the model, this is the purple or pink line shows the approximate multiplier confidence distribution in the prediction. So if you can see that for the approximate multiplier, more than 75% is classified with a confidence of 80 or more. But for the exact multiplier, only 20% is classified with a high confidence. Okay, so that's what we looked at first at the confidences, how they change, and then we tried it like what is the impact just at the accuracy? There is no attacks, just on the benign data. And then we show that there is like minimal impact in the accuracy. So we tried LeNet 5, which is a small network, and then AlexNet, which is a bigger network with multi-classes on Cipher 10. And we saw that there is minimal impact in the accuracy. So you still have accuracy drop, but it's like really minimal. Okay, now, sure.
Let me know if you're already answering it in the future slides.
Sure, yeah.
Do you retrain your model with your approximate circuits, or do you
No.
just take and retrain model?
So yeah, one of the features is that we don't retrain.
Okay, then I guess my question is about why this is increasing the security, because in randomization-based defenses, it's easy to understand it because you add dynamic randomness, right?
Yes.
Into the computations. Whereas in approximate computing, everything is static, right? So there is no...
For this approximation, we'll talk next example is dynamic approximation, but we'll, yeah. For this one, yeah, I got your question. And that's why actually I showed the confidence. I showed the confidence. So what we predict happened is that since the model is more confident about the decisions, okay, it's now harder to make it change its decision. And when we talk about white box attack, this is obvious. We'll show the results, and this is obvious that now, you know, if you have access to everything, you still can fool the model, but you need more noise. And that's what we showed. Like, you know, when you use our defense, you need more noise compared to regular one to be able to fool the detector. Okay. Sure.
What does confidence of a decision mean?
So like if I say this is a car, I can be 60% confident and can be 100% confident.
Right. But with the CNN, like how do you measure that?
It gives you that as an output. So I don't measure. So you have before the softmax, you'll give the confidence, and then the softmax will give you the classes. So these probabilities, you see these probabilities are the confidence basically. So and the highest confidence, I take it as the class prediction. So does that make sense?
So what's the difference between the prediction, class prediction, and confidence?
The class prediction is label. I say this is a car, but how confident I am that this is a car is this percentage.
How does the network know that?
So in the network, you have after the softmax, you get the probabilities. Then you convert this, the highest probability, you take it as a label and say this is a car. This is how like internally it works. Before you see it's a car, it will say, you know, it's 90% a car, 10% it's a cat, and so on. But then you'll see this 90% is the highest probability, then you'll say it's a car. Then you mark the label. Okay. Okay, so now we did security analysis. Now we saw that it doesn't have on the regular accuracy, you know, it doesn't drag down the accuracy. So now we tried like security analysis. So the first scenario is a transferability attacks, where we assume that the attacker knows the model that you're using, but does not know that you run it on this hardware, right? So imagine like you're using a service in the cloud, you know which model, but you don't know that it runs on that specific hardware. So the attacker can generate adversarial example on an exact hardware, and then try to see if this example would transfer and fool the approximate hardware when you run the classifier next to approximate hardware. So we tried, you know, all the attacks that are, you know, possible. And then we showed that for the exact classifier, you know, we're able to generate samples to 100%, you know, fool it. And then we use these examples and see if they work on the approximate classifier. And then we can see that, you know, that the approximate classifier is robust against transferability attacks. So, so from 100%, for example, here, like 38% was able to be misclassified, and then the other were not. And then, you know, in other examples, we have, you know, until 17%, and here, like there is 1% that all were misclassified. Now, the second attack scenario is called black box, where the attacker does not know the model or the hardware. And we talked about the reverse engineering in the previous paper, where we give inputs to the black box and take the outputs, and we train a substitute model. And then we use that model to do the attacks. Okay. And then we were able to show that still, like, you know, when you use the approximate multiplier, you're still robust against these adversarial attacks. So there is the last scenario is the white box attacks, where attacker know the model and know that you're using the approximate hardware, and they have access to it. So they generate the adversarial examples while running the model on the approximate hardware. Okay. So in this case, you can't know, you always can be, you can basically change a car, right? If you add the noise, like you have an unlimited budget of noise, you can change the image of a car to a cat or a bus or anything, right? So, so in this scenario, how we evaluate the robustness of the defense is that if in order to fool the defense, you need to add much more noise, then this defense is better. So, and we showed that, for the approximate multiplier, you always need to inject more noise compared to the exact multiplier to be able to fool the approximate multiplier. And this also approximation, right? Approximation is widely used for fault-tolerant applications to optimize their performance and energy efficiency. So we got these benefits also in addition to security. So in energy and also in on latency, you get a lot of benefits, and then energy delay product. Okay, so it's more efficient to use approximate computing, and it's also give you security advantage. Then we also use this approximation ideas for privacy-preserving machine learning. So also machine learning models sometimes are trained on private data, right? Whether it's clinical records, genomic data, location trace, or financial records. But there is this new attack that target this private data that the model is trained on. It's called membership inference attack. And in this attack, it's a simple question. So was the model, okay, a specific model, trained on the specific example? And it tries to answer this. I give it an example and a model, and I ask it, is this example part of the training data of this model or not? Okay. So how this attack work in terms of methodology, there is different attacks that uses different attack features. Basically, they look at the logit, confidence loss, or label, or a combination of these, okay? And then they showed that if the sample is part of the training data, it has a different distribution in this attack space feature than the data that the model was not trained on, okay? And then some of them use thresholding, and some of them train an attack model, and then use it for distinguishing. We call them member from non-member. Member is part of the training data, and non-member is not part of the training data. So why you want to do this, right? Why you want to ask this question, like, is this part of the training data of a specific model or not? It can be curiosity, right? You want to see if your data was used by Google, right, in their model or not. It can be, sometimes if you know, then you can come up with better attack strategies to re-attack this, do different attacks for that model. It can be data extraction attacks. So you have a competitor that you want to build a similar model to them, so you can extract their data and build your own model. And then for auditing, right? So, in court, someone says, they use my data and they want to investigate, they can use it for auditing as well. Also, there are many defenses in the malware in the machine learning community against these attacks. So we can categorize them into differential privacy, where you add noise to the training data itself, and then you train the model. But this lowers the accuracy drastically on the regular data. We have regularization-based models, but also they result in lowering the accuracy. We have output obfuscation models, but the adaptive attacks showed that you can, the label attack, we showed like different attack features. So the label attack was introduced after this defense to show that this defense failed to protect the privacy against label attacks. And then we have the most recent ones is DMP and Selena, and it's distillation based. So these guys kind of similar to the RHMD, where they train different models and like diverse models, and then they pick one randomly at runtime to do the prediction. But when you have different models, then it's higher, you require higher computation to do the training, also the inference. So we try to think about now, how can we leverage also approximate computing to do this, the best like state-of-the-art defenses using hardware support. So we leverage approximate computing to enhance now the robustness against membership inference attack by now injecting stochastic noise within the model computation using undervolting. So what is undervolting? Undervolting is basically reducing the supply voltage below the nominal voltage for the circuit. So when you undervolt, there is first is a guard band where even if you undervolt without changing the frequency, of course, you still don't see errors, but there is a region where once you undervolt in that region, then you start to see timing violations in the circuit that manifest as bit flips in the computations. So we were able to show by this approach, we were able to get higher utility privacy trade-offs, but also we reduced the energy consumption. So how we did this framework? So we got an FPGA and we got a voltage controller for that FPGA. And we were able, like this gives you an interface to only intervolt the compute the units in the FPGA, so not everything. And then we use this, we wanted to try, the undervolting when we get, machine learning models that run it. But, the accuracy drop was, so high because we can only undervolt the whole network, like all layers in the network. And then, like, if a fault happened at the output last layer, then, it will change always the output, and it was hard to control. And the other challenge that we face is that, the machine learning libraries that, they give you bit streams that you put in the FPGA. So it was hard to, identify a portion, like a layers, specific layers to undervolt. So what we did is that we tried to extract the fault model from the FPGAs, and we were able to model it in the software. So what is the noise model? And for us it was like a Gaussian distribution with a specific standard deviation. And this results show that we were able to extract it. Now we carried on the experiment exploration in the software. So basically we explored when we change how many layers we inject the stochastic noise, and then the standard, the deviation for the noise. What is the effect on the accuracy? And this, what is the effect in utility? Okay, and we see that as you increase these two, okay, privacy becomes better because you want privacy leakage to be the least, right? Least, which is 150%. If you reduce the privacy leakage to 50%, then the output does not make, it's like a coin flip, right? The output of the attack. And then, but you also want the utility to be as high as possible. Okay, so we have this, we solve this as a multi-objective optimization problem, to get the Pareto front for solutions for privacy utility trade-off, and we pick the one with the highest utility. And then, we experimented with different data sets. These are like, all prior works experimented with these data sets. We carried on using these data sets for the attack. And then, as you can see, like our defense compared to the others is doing better or comparable. But, our goal is not here, right? Our goal is to, we don't want to beat them in terms of our privacy because they're good in terms of privacy. We want to be within, within the same range, but we want to show that, we can lower the computational overhead and also save energy. So we can see that, as long as you're around 50% range, you're good, because from the attacker perspective, is like, all the work that they did is like, coin flip to say that this is a member or not. And then we started to investigate why, this works. And then this is the unprotected model. You can see for members and non-members, the data distribution, at least in the confidence space, they have different distribution. But when we applied our protection, these distributions overlap, and that's why we see the privacy is working. And also we tested utility, right, which is the accuracy. And for our defense, you have, compared to other defenses, we have minimal. This is the red one is the baseline, which is no defense, and then the green one is our defense, and the rest are other defenses. And we can see we have minimal impact on the accuracy. Okay, and we investigated why we have minimal impact in the accuracy. So we plotted the top 10 confidence score, for different models, and then we see that the highest confidence is still like distribution is still the highest confidence, and there is this small overlap with the rest of the distributions that resulted in the accuracy loss. But in the rest of the confidences, there is more overlap that impacted the attack features to be able to perform the attacks. So we compared the accuracy, utility or accuracy privacy trade-offs compared to other attacks. And then, this is the classification accuracy and membership inference attack accuracy. And then the best attacks are in this corner, the lower right corner. And as you can see, we're doing better or comparable to other defenses, but we don't use computations as they did. And then we also reduce the energy consumption. So with this, I'll conclude. So we have, I think this is an interesting research area at the intersection of machine learning, architecture, and security. So I showed 3 examples, one for attacking and protecting machine learning models using computer systems. I also showed an example for efficient security defenses for machine learning using hardware support and efficient privacy defenses for machine learning using hardware support. And I think there are many other research cross-pollution possibilities among these research areas. Thank you so much for listening to my talk, and sorry for taking more time.
Right, well, any questions for our speaker?
Yes.
Yeah, so you're talking about approximate, and you presented the upsides of higher privacy, better energy consumption, and minimal loss in accuracy. Are there any other downsides to approximate?
You can't apply them to non-fault tolerant application. So the application needs to be fault tolerant so that you can apply approximation to it. But if it's not, then this noise will always give you a wrong output, and you can't get benefit out of it. Like if it's a calculator, for example, you can't say 2 + 2 and it gives you 5, right? It's an approximate output. You can't make use of it. But for machine learning mode, it's fault tolerant application, so it handles, it's okay to do approximations for them. Any other questions?
Actually, a follow-up on that.
Sure.
I agree that machine learning inherently tolerant, errors. That's why people use low precision multipliers or adders, whatsoever. Right?
Yes.
Just a few bits.
Yes.
But I thought this kind of error, you needed to take care of it during the training phase. Right?
Yes, usually in the software-based randomization, they do, for example, random dropout, where you drop neurons from, but for them it was when they do this during training, and then they use it at inference to be able to keep up with the utility. For this one, we're still trying to think, to achieve theoretically why without retraining we were able. And the most, what we reached so far is because this specific multiplier, it adds more noise to as the 2 values that you want to multiply increase. So that makes the model more confident. So we're not making, when the values are high, you'll get high confidence, but we're making it even higher. So we're not changing, the output of multiplications rather than magnifying them. Does that make sense? Yeah. So if you see the noise distribution, it doesn't go down. It always goes up. So you just add, and the magnitude of the noise is, just additive, and it's correlated to how the 2 values you want to multiply are. Like if they're high, then you get more noise. And we're trying to see is this, can I just do this, right? Like when I have 2 values that I multiply, can I just make it the multiplier, even in software? Do higher value, and then you always get same accuracy and then better robustness, or not?
Yeah, so that's sometimes I think it's a little bit counterintuitive. That's why I would say
yes,
if there's some kind of theoretical analysis to show, if we can use this, and then you can get all this nice benefit.
Exactly.
Really nice.
Yes.
Otherwise, especially when I'm talking about these mission critical.
Yes.
These workloads, it's a little bit hard just to say, okay, let's lower the voltage.
Yes.
Right? It's
yes.
very dangerous.
Yeah, I totally agree with you. That's why we're trying now to investigate that. But I'm not a theory background, but we're trying to, now we're collaborating with theory people to now understand and even come up with AutoML to design the hardware. Like what is the best approximation to use for a specific model? That's what currently we're working on next. Yeah, awesome, thanks. Yes.
So as far as attacks, we're trying to work backwards to the labels. A lot of machine learning models, when they deploy them, they quantize the values. Does that have any impact on an attacker's ability to work backwards on those labels?
No, because like, at the end, you're trying to extract the functionality. You mean the reverse engineering, right? Component, yeah. So it doesn't matter if they're quantized or not, because I see them as a black box. And what I'm interested in is the behavior, right? So as long as I can model their behavior, I don't care if I'm not quantized and they're quantized. If I'm using, neural network, they're using decision trees, I don't care, right? As long as I can capture the behavior, right? Like when I give an input, how it will be classified, as long as the reverse engineering model behaves similar to that targeted model, then you're good. So you don't have to drive their specific models that you're using. You don't have to drive if they're doing quantization or not. Does that make sense? Okay.
Right, I guess for the sake of time, maybe we can stop here and let's thank the speaker again.
Thank you so much.